Today we want to talk about vectors. Talk a little bit about vectors. Last time we talked about projectile motion. We took a vector and we said there's some horizontal stuff and some vertical stuff. So that was breaking a vector into a component. But now we want to talk about it more generally. Sometimes we need a quantity with a magnitude and a direction. Magnitude is not enough. We need some kind of direction along with it. What I mean is we're making quantities that are different than scalars. So real numbers are scalars. In the context of vectors, scalars are just magnitudes, just amounts. Vectors have a magnitude and a direction. Vectors have magnitude and direction. We usually represent vectors with arrows. We usually represent vectors with arrows. The length of the vector, the length of the arrow that we draw, is an indication of its magnitude. We give our vectors one-letter names, just like we give our scalars one-letter names. But we want to make sure that everybody's clear that we're talking about a vector. So when we're talking about a vector, we put a little arrow over the top of it. Sometimes if we're typing the name of a vector, we'll put it in bold print. But since when we're writing, we don't really have bold print, we just put an arrow over the top. So vectors get one-letter names with an arrow over the top. Usually they're also not italicized, but that depends. Vector names are one letter with an arrow on top. The magnitude of the vector is the length of the vector. So the magnitude of the vector is the length of the vector. If we want to write down the magnitude of a vector, we put it in extra absolute value signs. Because absolute value is a specific kind of norm, a specific length. So the absolute value of a number is kind of like the length of the number, its distance from zero. So the absolute value of 5 is 5. The absolute value of -5 is also 5. It's just how far are we from zero? So in that way, it's the length of the number. So here we have the length of an arrow pointing off at some direction. So it makes it different than just an absolute value. Note that the magnitude of the vector is a scalar. So the length of this vector is just the number, that's the magnitude of the vector. The vector itself has this magnitude and it is at this direction. Part one, vectors have magnitude and direction. We denote vectors with the one letter name and an arrow on top. And we put double absolute values around it to indicate the magnitude. That's the length of the vector. So that's how we indicate the length of the vector, the magnitude of the vector. We need to indicate the direction. So let's talk about the direction. We have a few ways to indicate the direction of a vector. One, we could use an angle. And we'll put this angle in standard position. So angles counterclockwise from the positive x-axis. The other way we might do this is using horizontal and vertical components. We're not always going to be in standard position. I suppose if we have something like heading, then that would be different than standard position. But we might denote the direction of a vector with an angle or with horizontal and vertical components. So I might describe this vector v as being with a magnitude of 5 at an angle of theta in standard position. So I might describe the direction of the vector B as being at an angle of theta, and then I just describe the magnitude. I just tell you what the magnitude is, and I tell you the direction of the vector. The other way we do this is we break the vector into horizontal and vertical components. So that is, we may use multiples of these unit vectors. So we'll describe the vector with how many horizontal units we have and how many vertical units we have. When we write down a vector, we want to distinguish this from a point or an interval, so we put it in pointy brackets. So we write vector components in pointy brackets. When we're writing a vector, and we're just going to list the components, we put that in pointy brackets. This I and j are our basis vectors. So we describe a vector v as, say, some combination of these basis vectors. The basis part, it means the following. We use I and j as a basis for describing two-dimensional space. Every vector in a plane can be described as a unique combination of these vectors I and j. This doesn't happen if we use theta, because theta equals 30 is the same direction as theta equals 390, or theta equals negative 330. So we might describe this vector v as 4, 3. Because we went 1, 2, 3, 4, I, and 1, 2, 3, j. So when I say vector B is the vector 4, 3, I'm listing the components. I'm writing it as a linear combination of I and j. It is 4 of the vector I and 3 of the vector j. With 1I, 2I, 3I, 4I, 1j, 2j, 3j. We have these two descriptions using an angle or using a horizontal and vertical components. We should be able to switch back and forth between the two. And we have just drawn a right triangle, and that is how we will go about this. Notice that the length of the vector is going to be the hypotenuse of our triangle. So here's 4I down here. And here's 3j up here. The magnitude of the vector v is going to be the hypotenuse. The adjacent side is going to be the I component. And the opposite side is going to be the j component. So if we want to translate between the two, the adjacent side will be the hypotenuse times the cosine of theta, and the opposite side will be the hypotenuse times the sine of theta. And at this point, we notice that we're just doing the problem that we did on Monday backwards. Instead of starting off with an angle, a vector at some angle and breaking it into components, here we have two components and we're writing down what the vector is, and we're figuring out the magnitude and angle of the vector. Pause here for a moment and come back and talk about vector operations.